Good morning.
Good morning, sir. Good morning. We'll start within a couple of minutes, sir.
Oh, surely, surely.
Yes, sir.
Please.
Good morning, all. Welcome to the fifth day of Atal Academy sponsored Faculty Development Program on Computer Science and Biology. Today's session one topic is computational techniques in chemical engineering, and the speaker is Dr. V.S. Sapkal, Professor, Department of Chemical Technology, Sant Gadge Amravati University, Amravati. Now I request Dr. S.L. Bhagat sir to introduce the speaker.
Good morning to one and all. Today we have our eminent speaker, Dr. V.S. Sapkal sir. He started his career as a technical director at a German company, Sartorius, a membrane manufacturing company. He has completed his PhD and MTech from IIT Mumbai. He has served as a professor and HOD from 1995 at Amravati University, Amravati. He had also been appointed as a Vice Chancellor for Nagpur University, and he has also served as an acting Vice Chancellor for Sanskrit Vidyapit, Ramtek, Nagpur, and Amravati University also. He was nominated as an expert by President of India for selection of professor in chemical engineering at IIT Mumbai. He was nominated as a chairman at All India Board for PG Education and Research of AICTE. He was also appointed as a chairman for the Standing Appealing Committee of AICTE. As an academician, he has guided 35 MTech students and 15 PhD students. His technical, industrial, and teaching experience of 30 years will be very fruitful to us in today's talk. I welcome V.S. Sapkal sir for today's talk.
Can we start?
Yes, sir.
Yes. Thank you.
Thank you, sir.
Yes. I'm really happy to be with you today, Patil sir, Bhagat sir, and all the participants of this faculty development program sponsored by AICT. The theme is extremely important. As you know that any chemical process industry is basically always looking for three things. One, productivity improvement, enhancement of quality, and becoming more and more economically viable. Rather, to become more competitive in the market, every chemical industry looks for the areas for improvement, modification, and also tries to save the resources, tries to avoid the losses, tries to recover the useful products from the waste for recycling or for reuse and so on. As you know that the chemical industries are now shifting from conventional chemical processes to the processes based on using renewable feedstock, using the technology which is more combination of biological science and engineering, and also producing the product which are biodegradable. That means after the use of certain lifetime, the product should be again disintegrated to its original components so that it can be recycled back. This paradigm shift in chemical process industry is also very important as far as the cost of production is concerned. As you know that after the product is manufactured in any chemical process industry, or for that matter any reactor, the product is required to be separated from the unreacted reactants, byproducts. After separation, it is required to be purified to the desired level, and it is to be then concentrated, and so on. And these all processes, separation, concentration, purification, fractionation, is called downstream processing. And as you know, in chemical industries, the downstream processing contributes about 70% of the total production cost. That means in the upstream processing, the preparatory part of any reaction, for that matter, preparation of reactants and bringing all the reactants in certain composition under certain conditions in a reactor, and then controlling the reactor with the help of precise control and measurement of parameters, so that the reaction kinetics and thermodynamics happen in the most optimal condition, and the reaction is close to the stoichiometric ratio, and then the product is formed. However, even if after using catalyst and other assistants, the production is up to certain level. And as you know that the most important aspect after the reaction is over is recovery of the product. And recovery of the product is the complete task of downstream processing. In downstream processing, whether it is simple rotary vacuum drum filtration or plate and frame filtration, centrifugation, chemical precipitation, distillation, extraction, humidification, crystallization, chromatographic separation, and there are a number of such operations including membrane technology also. It contributes, there are a large number of stages in downstream processing. And as you know that every step you use in downstream operation for separation of either the required product or for concentration purpose, purification purpose, every step consumes some energy as well as efficiency. Say for example, the filtration, the first stage is 90%. That means 10% is already lost. Even if you use the most efficient equipment as well as process, still there is loss. Second stage may be the centrifuge. So centrifuge also 90% recovery, 90% of earlier 90%. That means you keep on losing some product due to the number of stages, and in downstream processing, sometimes the product recovery is as low as 30%. But you have already paid or incur the cost of the production, and hence the production cost goes up and the competitiveness in the market is considerably challenged. And hence in the downstream processing, I have started the discussion. Before we come to the focus point, I am bringing you the advantages of a certain technology and then how we can talk about the recent advancement of this technology. So I was talking about downstream processing using large number of unit operations, chemical unit operations, and more number of stages you use, the recovery of product is considerably low, and hence the trend is to combine the 2 or 3 stages in single stage, making a hybrid system or hybrid technology. And this technology can be effectively reduce the number of stages, and this number of stages can be, for example, like reactive distillation or extraction in 2 stages or centrifugal extraction and so on. That means the combining the 2 or 3 technologies together, bringing the benefits together and eliminating the number of stages and hence the capital investment cost, the processes used to be optimized or intensified. However, this trend was still taking lot of energy cost as well as production cost. On the same line, membrane technology has come in picture. As you know, that with the development of specific structure That means pore size distribution, and physicochemical structure of either polymeric membrane or inorganic membrane has considerably influenced the design of downstream processing. In the first stage, for example, now biological process, as I told you that most of the chemicals are now manufactured by biological processes, and hence it is called fermenter or biotechnology or biochemical processes, where you use the either bacteria, algae, fungi, and there are different types of strain to produce, whether it is fermentation or acid manufacturing or protein, antibiotic, everything is manufactured in fermentation. And after the fermentation is over, in the downstream processing, as you know that in manufacture of any pharmaceutical or biopharmaceutical product or chemicals also, large number of operations are used in downstream processing, and hence the membranes are coming in picture. As you know that most of you are aware of membrane application in water industry, whether it is desalination of water or wastewater treatment for achieving the for achieving the pollution standard, removing all types of pollutant, and also recovery of useful products, and most important is recovery of water for recycling. As you know that this technology is more after three aspects, more important in three aspects. One is it not only helps to control the pollution and hence the environmental protection, but it has help in recovery of useful byproducts and also recovery of water which is recycled back for reuse. And hence these three aspects have made this technology very, very attractive. And as you know that the separation in membrane technology is at ambient temperature. There is no phase change, and hence there is no requirement of phase change, that is latent heat of vaporization for separation by phase change. And hence it is a energy saving technology also. After understanding the mechanism, transport phenomena, as well as mass transfer through membrane, it has now applied to all the different types of separation, concentration, fractionation operation in almost every industry. And in downstream processing, it has become a alternative, very technical and economic alternative in downstream processing in chemical process industry, replacing large number of stages. It has replaced filtration, it has partially replaced distillation, it has completely separated centrifugation, extraction, and so on. So basically, after understanding the membrane science, technology, and engineering, the structured membrane can be developed for specific application. That means for specific separation with respect to molecular size or molecular weight, or the product which is whether it is to be concentrated or whether it is to be separated from the impurities or whether the recycling is required. And hence, as you know that the membrane technology has come in different forms, shapes, size, pore sizes, and processes. Whether it is nanofiltration, ultrafiltration, microfiltration, or reverse osmosis, there are different types of membranes which are either made up of polymer material like polysulfone, polyolefin, polyimide, or for that matter inorganic membrane like ceramic membranes. And the processes based on membrane, whether it is pervaporation, membrane bioreactor, or membrane distillation, for not only aqueous separation but also non-aqueous separation, and for that matter gas separation. Hence membrane technology with different forms and processes have come in picture to replace the conventional chemical processes as well as chemical operations. And hence when we talk about considering now the just a minute, I will just make the presentation. Can you see the slide? Can you see the slide?
Yes,
Yes,
sir.
sir. Yes,
Yes,
sir.
sir.
You can see, sir. It is visible, sir.
Okay. So when we talk about yes, I was talking about membrane separation processes, and considering the theme of theme of this FDP. Now, as you know that membrane, it is visible, right? The slide is visible.
Yes, sir. It is visible.
Okay. As we can see that the membranes are specified for three things. One is its physico-chemical structure on the surface, as well as its pore size distribution. Similarly, its physical properties, chemical properties, and biological stability are required to be studied in depth, which has been already done for specific application. But however, most of the time when the membranes are used for separation or concentration application, there are two important problems that this process face, and one is concentration polarization and fouling of the membrane. As you know that even if the membranes are used on the cross flow filtration system, that means, as you know that conventional filtration where the feed is perpendicular to the filter element, and the particles or impurities are retained on the surface of the membrane, forming the cake, which subsequently offers resistance to the filtration or passage of the filtrate through the filter, and hence slowly there is decline in the filtration rate. However, membrane filtration system works on tangential flow filtration. That means the feed is between the two parallel membranes, and they are basically feed is divided into two parts. One which is passing through the membrane, which is called permeate, and one which is recycled back, which is concentrate. Hence, feed is divided into feed and concentrate because the feed is at the tangential velocity over the surface of two parallel membranes forming the channel. And because of this mechanism, hydrodynamic mechanism, the impurities or the product which are separated from the membranes are not allowed to sit on the membrane surface, but they are taken away from the membrane surface. And as you know, the channel which is formed between the two parallel membranes are basically increased, the turbulence is increased by putting the spacer in this channel of the membrane, and further it improves the cleaning effect or separation performance of the membrane, and hence the permeate rate is maintained at a desired level for long time, because the membrane surface gets cleaned every time because of the tangential velocity of the feed over the surface of membrane. As you know that the driving force in membrane is transmembrane pressure across the membrane. That means the feed is basically having the, when it enters the channel, it has the higher pressure, and subsequently down the line the pressure in the channel gets reduced, and then which is recycled back, and hence across the membrane it is called transmembrane pressure. That means average pressure of inlet pressure, that is feed pressure, and the retented pressure, average of this is called transmembrane pressure, and the permeate is at the atmospheric pressure, and hence it is the operation takes place. However, as you know that membrane performance depends upon how the membrane surface behaves for particular application, and hence the characterization of membrane is extremely important. As you know that the membrane is designed and developed for a particular application, need of that application, whether it is low molecular weight separation, whether the separation is at lower temperature, or whether it is at very high pH range, and so on. So basically the membrane structure and properties are developed depending upon the application of the membrane. And hence when we talk about concentration polarization or fouling effect of membrane, it is required to be characterized with different techniques, and one of the main technique is computational characterization of membrane, which is very important. As you know that there are different modules, there are simulations and studies to understand how the fouling takes place over the surface of membrane, how the membrane behaves over a period of time with specific interaction between solute, solvent, material, what is the surface morphology of membrane, and also what is the steric and non-steric and polar effect of membrane. As you know, membrane is not just sheer filter. It is the resultant of the interaction between solute, solvent and polymeric material, which will decide which component in the feed will get preferentially sharp over the surface of membrane and which will get through the membrane through the diffusion capillary, and it is called preferential sorption capillary flow mechanism. Hence, the membrane is a typical mass transfer operation under driving force of pressure and concentration gradient, and it is under the dynamic condition. That means the feed is constantly flowing over the surface of membrane, and hence it is the physicochemical interaction between solute, solvent in presence of polymeric specific material will decide what component will pass through the membrane and what component will be retained by the membrane. And hence, the characterization of membrane is extremely important. And when we talk about analysis of performance of membrane, the characterization of membrane before use and after use to understand the property of material at atomic scale is done by computational characterization. As you know that the computational characterization, modeling simulation, creating the data which is required to be validated with the experimental data is very important. And the understanding of fluid dynamics is very important in membrane application. As you know that the membrane performance depends upon how the fluid dynamics is controlled over the surface of membrane. As you know that the membrane modules are of 4 types. One is plate and frame type of membrane, in which there are parallel sheets of membrane and the feed is passing through the specific channel between the 2 parallel sheets of membrane. In hollow fiber membrane, there are number of fibers put together and the feed is between the core of the fiber and the permeate comes out of the fiber on the shell side. However, there can be hollow fine fiber. That means the feed is from outside the fiber and the permeate comes out from the core of the fiber. Then another type is tubular type of membrane module, in which the membrane is put into the forms of different tubes, a bundle of tubes in the housing, and which has the flow is again through the tubes and the permeate comes out of the surface of the tubes. And the most widely used is spiral wound model. That means the 2 sheets of the membranes are sealed together with the spacer in between them on the 3 sides, and then it is rolled over a pipe, perforated pipe, creating the spiral design. The flow is flowing through the spiral form, and finally the permeate enters the perforated core tube and comes out. That means depending upon the flow dynamics, the selection of module takes place, whether the feed has more impurities to handle. In that case, the tubular module is better in that case because it has a better handling capacity for impurities concentration. And hence, if it is a very specialized application, normally the hollow fiber membranes are used. And hence, we have to understand the fluid dynamics with respect to individual membrane module performance and maintenance of the permeate rate under the certain condition. Similarly, as you know that these membranes are widely used for separation of proteins. And as you know that the proteins are high value product. These proteins, while separation or purification, gets absorbed over the surface of membrane. And hence, the characterization of membrane is also important with respect to the study of adsorption on polymeric membrane surface. Because the adsorption also decides how much is the concentration, polarization, and fouling effect, as well as loss of very high value product over the surface of membrane. It also decides the cleaning frequency of the membrane. If the adsorption is, whether it is reversible or irreversible type of adsorption, and subsequently whether this adsorption can also decide the cleaning frequency of the membrane. This is also very important as far as the continuous design of the membrane is also concerned. Sometime by reversing the flow during the operation itself reduces the adsorption layer on the surface of the membrane. And as you know that this adsorption layer which contains useful product is required to be recovered, and hence the characterization to study the adsorption on polymeric membrane through computational technique is equally important. As you know that there is a very close interaction between the solute molecule. As you know that we can separate the molecule having low molecular weight as low as 50 molecular weight or 50 daltons, or the proteins in maybe 1 lakh molecular weight or 300,000 molecular weight. But there is an interaction at sub nano and nano scale. As you know that the separation depends upon the interaction between solute and the membrane material, and hence the interaction has to be characterized for understanding the adsorption. And hence the nano and nanoscale surface interaction between solute and membrane is extremely important, and that is done again by computational characterization of membrane. These all aspects also makes very important sense as far as the immobilization process is concerned. As you know that membrane surface is widely used as carrier for immobilized catalysts. Many protein molecules are immobilized on the surface of membrane, and this is used as biocatalyst in most advanced system of bioprocesses. The immobilization kinetics is extremely important, and that is again helpful for understanding the nano and sub nanoscale surface interaction along with the system. So kinetics and performance prediction of mixed matrix membrane. As you know that the membrane materials are widely used for different, as you know that if the application demands for wide range of temperature operation as well as operation with wide range of pH, hence the different types of membranes are mixed together, whether it is thin film composite membrane of polyamide on polysulfone and so on, and hence this computational characterization helps in predicting the performance of mixed matrix membrane. The membranes made up of different polymeric material under certain conditions and composition having specific biochemical properties, chemical and physical property. And as you know that the transport property characterization of membrane is also done by computational characteristic. As you know that the membrane is performed with respect to specific selectivity and permeability. If you see that the large number of studies have taken place for computational modeling and simulation of membrane, particularly not only for aqueous application, but also for gas separation. As you know that the methane separation from CO2, or for that matter CO2 capture and sequestering, membrane plays extremely important role, and hence the membrane structure should have not only selectivity and permeability but relative selectivity from the mixture of the gases, and hence there should be analysis of relationship between molecular structure and their gas transport properties. As you know that we have to understand from the mixture of gas which gas will get more selectively permeable or transport through the membrane will depend upon understanding the relationship between molecular structure and the gas transport properties, and we have to understand the accurate gas diffusion coefficient through a particular type of membrane material, with respect to the mixture of gases. As you know that the separation performance depends upon nanocomposite membranes. As you know that the separation performance sometimes is enhanced by also making nanocomposite membranes. That means whether it is MgO or for that matter, there are a number of nanoparticles combined with the solution of membrane through which the membrane is produced or cast. During the composition of the casting solution is changed to incorporate the special characteristics of the membrane structure or membrane surface structure, and hence which will enhance the selectivity and permeability of membrane for particular gas, and hence nanocomposite membranes are widely used. And for that matter, again the study of computational characterization is extremely important for composite nano composite membranes. As you know that the both gas dynamic, fluid dynamics as well as liquid is extremely important in order to understand the effect of transmembrane pressure on the membrane structure and transport property. The characterization involves the investigation of fluid dynamics. That means the fluid which is flowing over the surface of membrane is to understand the effect of transmembrane pressure, not only on membrane structure, but its transport property or its performance. Under transmembrane pressure, how the membrane, whether there is a compaction effect, which is irreversible effect due to high transmembrane pressure, which is irreversible. And hence, we have to not only understand the fluid dynamics, but the combination of fluid dynamics, that means fluid flow operation in the channel of the membrane, along with the specific transmembrane pressure. These combined two properties will decide impact of these two properties on membrane structure for long-term process, as well as its selectivity, that means rejection efficiency and transport property. How much is the, as you know that the transmembrane pressure is a driving force. Higher is the transmembrane pressure, higher will be the flux or permeate rate per unit area of membrane per unit time. But if we increase the transmembrane pressure beyond certain certain level, certain value, then it gives impact effect on the membrane structure, and this membrane structure gets damaged, and which will then increase the cost of replacement of membrane. And hence this investigation of both fluid dynamics and transmembrane pressure on membrane structure and transport property is extremely important. As you know that there are computer-aided approaches which contributes not only to strengthening the fundamental research in this process, but also it helps a more successful exploitation of membrane technology in industrial application. While we do all these characteristics and understanding this investigation, studies, and so on. Basically, see, if you have some question, you can ask right away. Hello? Hello?
Yes, sir.
Yes, if you have some question or some doubt, you can ask the question during our discussion itself. Okay?
Yes, sir.
Okay. So we have to understand that the membrane application is made viable or attractive or alternate technically and economically to the conventional only if it is optimized, it is designed, and it is implemented in the most technically optimized way. That means whether it is the selection of membrane material, selection of design of module, selection of the operating parameters such as uh, feed flow rate, transmembrane pressure, operating temperature, operating pH, as well as the selectivity and the permeability of the membrane. Based on this understanding, is possible to exploit more and more industrial application by membranes. Membrane, as you know that 50% of membrane application is in health industry, whether it is dialysis, whether it is membrane based sensors, or whether you name it. The health industry use the sterile filtration of ophthalmic, or for that matter any sterile filtration of liquid, gas, all these pharmaceutical and health industry, they are using very specialized membrane. As you know that if the membrane is to be used for producing sterile liquid, which goes inside your body as a injectable, it has to be sterile. And as you know that the conventional method of sterilization of any liquid is by heating it by the thermal process, which requires large amount of energy. Whereas zero point 0.2 micron pore size of the membrane ensures the filtrate which is sterile in every component, every aspect, whether it is biological, whether it is bacteria challenge test, sterility test, and so on. And hence, membrane has replaced number of process operations which are energy intensive, which are capital intensive, and hence more number of industrial applications are being exploited by understanding the uniqueness of membrane, structure of the membrane surface or the polymeric properties, as well as interaction between solute at nanoscale, and improving the performance of membrane by incorporating like nano components, and optimizing the parameters such as understanding the fluid dynamics, transmembrane pressure, and so on. So these membranes, with the help of computational characterization, can focus or can optimize material design for membrane application, structure property relation in materials for membranes. As you know that membrane material, there are large number of polymeric membrane materials available, but however, to transform them into the desired structure of membrane with respect to, say, asymmetrical structure, dense structure, thin film composite structure, as well as uh, whether the membranes are made up of different polymeric material, having specific molecular weight cutoff, or it can be characterized by retention ability for low molecular weight substance, or whether the surface can be modified using not only nano particles, nano composite, but also grafting, radiation, and so on. So basically, surface structure is extremely important to develop the specific property required for specialized application, whether it is very high value and low volume application in biopharmaceutical, or large volume, low value wastewater treatment application. So membrane material with structured and property can be developed by understanding the membrane material and its characteristic. Membrane morphology at nanoscale level is extremely important. As you know that membranes are to be characterized for its chemical stability. That means whether the membrane can withstand range of pH application, as well as whether it is having stability for different solvents, organic, inorganic solutions, and so on. Uh, Also, whether it has thermal stability, whether it can stand for long period, high temperature application without any impact on its structure. Third is whether the membrane can have the biological stability. That means if at all we are handling some micromolecule or microorganism, whether this has the impact on the structure of membrane, whether they, like for example, cellulose acetate membranes are required to be stored under formaldehyde solution in order to save it from the interaction with the microorganism, which will otherwise eat away the substance of the polymeric material. And hence the membrane morphology at nanoscale, whether the membrane structure is also characterized using electroscanning microscope or atomic force microscope in order to understand the roughness, pore size distribution at nanoscale level. Similarly, quantum mechanics and quantum chemistry is the outcome of computational characterization of membrane, which will not only understand the mechanics at micro level, but also interaction, whether it is irreversible interaction, preferential interaction, or for that matter under pressure, whether it is diffusional process that is taking place. And hence prediction and analysis of transport phenomena is the outcome of this characterization process using computational technique. Prediction and analysis of transport phenomena will decide which component at what flow rate is being transported through the membrane as permeate. And the molecular dynamics simulation is extremely important. As you know that the interaction at nanoscale with known membrane morphology, along with the data that we can have experimental data, or we can have the equations which are developed and which are solved, and then the results are then basically tested in or compare with the laboratory data. A non-covalent interaction in membrane is one of the most important aspects, particularly for particular application, and multi-scale modeling of materials for membrane science and engineering, along with modeling of membrane operation and membrane processes. As you know that once we know the area of membrane required to handle particular size, batch size in industry, then we have to design the number of membrane modules having that much area is required to be now developed, and that is membrane process and membrane engineering. And that is that whether the number of modules in series, in parallel mode, because the membrane can be operated efficiently with single pass, with multiple pass, with batch operation, with continuous operation, with feed batch operation, and so on. So membrane processes are required to be optimized. The computational fluid dynamic comes in picture very prominently in membrane application. As you know, the CFD is very well now established technique, and which will understand not only the interaction between the two components, whether it is from the mixture of the feed with the membrane material in presence of solvent. And this computational fluid dynamics will decide, will understand first the performance of the membrane, and based on the findings, the performance can be improved. The performance is normally improved by 2 or 3 ways. One is increasing the turbulence over the surface of membrane by way of incorporating spacer between the two parallel membranes. And as you know that these two system which will decide then you have the Reynolds number calculation, laminar and turbulence phenomena, and creating the basically reversing the fluid over the surface of membrane using the combination of different types of walls in engineering system. That means the feed one time the feed walls are open, the feed is from one end to another end of the membrane. At this, after certain duration, the flow is reversed with the help of walls. That means the concentrate or retentate becomes the feed, and the flow starts flowing from the reverse direction. That means the fluid dynamics in the channel of the membrane decides the impact of transmembrane pressure as well as the fluid dynamics over the surface of membrane, and that will improve the membrane performance. CFD helps to provide the best compromise between the pressure drop and flow velocity. As I explained, that the pressure drop in the membrane channel as well as flow velocity and the permeate flux for a particular module design with specific spacer. As you know that the turbulence can be improved by using specific spacer. Normally this is the what you call net is put between the two parallel membranes, and that will improve basically the transmembrane velocity, that is flow velocity, and which will reduce the fouling or concentration polarization impact on the surface of membrane under specific pressure drop. As you know that the transmembrane pressure and flow velocity need to be balanced in an optimized way in order to have the higher permeate flow for long time, and that will help in particular module design, whether it is hollow fiber membrane or spiral wound membrane, tubular membrane, or plate and frame type of. As you know that this is not enough. The computational fluid dynamics also decides one of the most high level of application in membrane, and that is membrane bioreactor. As you know that membrane assisted bioreactor, whether it is the secondary treatment is in bioreactor, activated sludge process and other thing, but when the membrane is incorporated in it, membrane bioreactor plays extremely important role in improving the performance of biological reactor. This is because, as you know that as the digestion takes place in biological reactor, membrane is used to withdraw the treated effluent using either suction. If it is two types of membrane bioreactor, one is submersible membrane, that means the membrane is submerged in the bioreactor itself, and the vacuum is applied on the permeate side of membrane, and the treated material is basically treated liquid is sucked out of the bioreactor, and that has increased the performance of bioreactor manifold. It has improved its sludge handling concentration capacity. It has reduced its footprint. It has improved its retention time. It has reduced its retention time, as well as it has given the product which can be recycled back into the process, either in the form of liquid or treated liquid. And hence submersible membrane, or there is another type of membrane bioreactor, which is external membrane bioreactor. That means the membrane system is attached to the bioreactor externally, and the treated sludge is pumped out of the reactor into the membrane system, which is recycled, which is treated with membrane, and which is recycled back into the reactor. Meanwhile, the permeate is taken out of the membrane, and this is the transmembrane pressure, as well as cross flow filtration that takes place externally. And this process is widely used for extracting the important components of the treated effluent, as well as recovery of water for reuse through recycling. And hence membrane bioreactor design can be optimized for the best performance in wastewater treatment using computational hydrodynamics in membrane and system. Many times it is calculated that whether the membranes are to be submerged in horizontal or vertical manner, because the hydrodynamics over the surface of membrane is maintained by way of, say, purging of air. That means aeration is taking place in the bioreactor. That means it is not only maintaining the oxygen level in the broth, but also it improves the turbulence in the liquid, and that turbulence helps in reducing the fouling of membrane over the surface. And hence this hydrodynamics, computational hydrodynamics, is used here for application in understanding the membrane performance in membrane bioreactor, as well as in the submersible bioreactor, as well as external bioreactor. As you know that effect of aeration, as I explained, on biological and membrane filtration performance for integrated membrane bioreactor is again done with computational hydrodynamics. And hence the computational techniques, whether it is simulation modeling, has made important in understanding hydrodynamics, in understanding nanoscale interaction between solute and membrane material, and effect of aeration on biological and membrane filtration performance. And this is done very widely in order to understand the agreement between experimental data and computational model data. The experimental validation is in good agreement with computational model. As you know that I was talking about the gas separation. Now membranes, as you know that, are equally used not only for liquid separation or aqueous non-aqueous separation, or membrane bioreactor for evaporation, membrane distillation process, where the higher concentration of separation is achieved. As you know that pressure driven membrane process has limitation for the concentration that can be achieved, which is normally 20 to 25% in reverse osmosis or ultrafiltration or nanofilter. But membrane distillation has made it possible to reach the higher concentration up to 60-65%. And that is possible, that is made possible because of the membrane distillation. Across the membrane, the temperature gradient is established, and because of this, the concentration gradient, the vapors are passed through the membrane, and which is subsequently on the permeate side is put under suction vacuum and then condense into the liquid. That means the temperature is much below the boiling temperature, and hence membrane is again not only for the dilute solution can achieve the concentration without phase change and saving the energy, but membrane distillation also helps in achieving higher concentration at again the lower temperature gradient, at the temperature which is lower than the boiling point, and hence it saves considerable amount of energy for achieving the desired level of concentration. The third application, as I mentioned to you, that in biological application as well as in health industry, membranes are widely used. And as you know that for gas separation, membrane contractor is widely used. A model can be developed for associated mass transfer and chemical reaction of gas with solvent in the contractor. That means membrane is a barrier between the solvent and the gas. The solvent, the gas is passed through the membrane and which reacts with the solvent. And this model is demonstrating the mass transfer and chemical reaction of gas with solvent in the membrane contractor. Normally, hollow fiber membrane technology is used for CO2 capture due to its high surface area per unit volume for separation and reaction, which is widely used for CO2. As you know that CO2 is greenhouse gas impact, and which is required now to be not only captured, stored, but also is required to be used for many important application, which is a good feedstock now for manufacture of many useful chemicals. If this is the interaction, not only mass transfer through the membrane, but in gas liquid hollow fiber membrane contractor, a feed gas is passed through one side while chemical solvent is passed either co-currently or counter-currently in the other side of membrane module. And because of this contact, the gas here also we have to use the membrane very selectively, which has higher selectivity and permeability of a particular gas in the mixture of the gas. And hence CO2 will get preferentially passed, that is mass transfer will take place through the membrane, and which will on the other side, the liquid, that is solvent, is flowing either co-currently or counter-currently. As you know that the counter-current is very efficient operation in the membrane module. And normally hollow fiber membranes are used, which is basically having very high surface area, and hence which can be used for higher concentration or large capacity of CO2 stream, and which requires less investment cost in the form of membrane module and system. Which is also, as you know, that the solvent is not the direction is important, concentration is important, or selectivity of membrane and permeability of membrane for particular component is important, but solvent velocity is also important over the surface of membrane. And hence the resulting gas separation in counter current model mode are optimized using experimental data and simulation data. A modern computer application, that is membrane optimization tool for modeling of gas transport of processes through mixed matrix membranes, which is based on the Maxwell model, can be successfully used to model gas transport through the simplest types of hybrid membrane. If we use the mixed matrix membrane, that means the membranes made up of different what you call different materials. Because why we bring together different materials? Because we bring the benefits of different materials together and overcoming the individual weaknesses or constraints. And when we talk about mixed matrix membrane, then its performance is very important for particular transport of gas. And hence, to understand this, we have to create the computer application membrane optimization tool, which is widely used again in membrane application for understanding gas separation. As you know that this is what we have understood, that membrane morphology at nanoscale is to be studied along with transport phenomena, fouling issue, process improvement and application. These are the main outcome of computational characterization of membrane. As you know that there are different equations, such as, whether it is starting from basic equation of diffusion through membrane using even the Fick's law, as well as considering the interaction, considering the direction, considering the selectiveness, considering the operating parameters, is all put together. The characterization of the membrane, either by experimentally, by whether it is chemical, thermal, biological stability, characterization with respect to the separation efficiency, permeability, with respect to instrumental characterization like its surface morphology, pore size distribution, and so on. So these will understand the accurate nature of the membrane and its transport phenomena, and whether it is susceptible to fouling issues, and whether we can improve the process by taking the corrective action in the form of engineering design to control the fouling, as well as expanding the applications of membrane after we understand the membrane morphology at nanoscale level. As you know that due to rapid growth in digital computation capacity and improvements in simulation algorithm, as well as parallel programming, simulation, modeling, have become fundamental tools for fundamental comprehension of transport phenomena and the priority prediction of permeation rate based on rigorous calculation of interaction of liquid and gas molecules with several types of membrane material are widely studied now. As you know that we have to understand not only the transport phenomena, but preferential, that means prediction of the performance of the membrane in terms of selectivity, in terms of permeation rate. Similarly, based on the interaction between the gas and liquid molecule is done in the computational capacity. As you know that this is not the only application, whether it is liquid application, gas application, membrane bioreactor application, membrane pervaporation and distillation application, but membrane has now come in picture with every unit operation, like membrane assisted crystallization, aiming to induce, as you know that the crystallization works on increasing the concentration to the level and then the supersaturation, and then the crystallization starts either by suddenly dropping the temperature or further evaporation of the solvent, and it triggers the process of crystallization. But membrane can now assist the crystallization, aiming to induce supersaturation in a solution, has been successfully tested in crystallization of ionic salt, low molecular weight organic acid and proteins. Membrane crystallization is an emerging membrane process with the capability to simultaneously extract fresh water and valuable components of various streams and to recover valuable minerals from highly concentrated solution. As you know that the concentration reached to the supersaturation level, and then membranes can be suddenly used for not only separation of the liquid so that the crystallization triggers and the liquid is recovered for reuse, and the minerals or high value products are extracted from the concentrated solution. This has replaced, of course, the conventional evaporation method is replaced with the help of this application. So basically, we have to understand now the application of membrane in totality with respect to understanding the morphology, performance, selectivity, and molecular dynamic simulation are used to study the crystal nucleation and growth of, say, for example, in this case, as I explained to you, that this membrane assisted crystallization has changed the crystallization process itself, which is a very energy intensive process. The conventional evaporation method is basically highly energy intensive, capital intensive, and it also operational difficulties. And hence, the membrane assisted crystallization has not only help in reducing the energy cost, but also its footprint and recovery of valuable minerals from highly concentrated solution. And not only it can only extract salt, but also it can also give the liquid which is recycled back, and that is possible through molecular dynamic simulations, which are used to study the crystal nucleation and growth of sodium chloride in bulk with hydrophobic polymeric sulfate material. As you know that the membranes can be made up of material which are hydrophilic in nature or hydrophobic in nature. Hydrophilic membranes are used for mainly aqueous application, that is filtration in terms of liquid, in terms of water, and so on. Whereas hydrophobic membranes are to be used for gas separation or for now oxygen nitrogen separation or methane carbon dioxide separation and so on, hydrogen separation. So basically hydrophobic membrane is required, because when you try to, say for example, air filtration in fermentation industry, where you need sterile air supply for the fermentation operation, the conventional method of sterilizing air was to use the depth filter column. That means the packing material made up of either glass fiber material, and the air used to be heated and then passed through this the fibrous material to achieve the sterility, and which goes into the ferment. But however, it was not a very safe operation. Sometimes the channeling effect of air through this depth filter, through the column of depth filter, used to risk the fermentation sterility, because if the air is not 100% sterile, it may give rise to the contamination. Whereas hydrophobic membrane, having say 0.2 micron membrane pore size, ensures the complete sterility of air which is required for sterile application in fermentation operation. And this hydrophobic polymer such as PBDF, PTFE, that is polytetrafluoroethylene, or polyvinylidene fluoride, or polypropylene at supersaturated concentration is widely used for membrane assisted basically crystallization. As you know that if you have some moisture in air, and if you try to filter through the hydrophilic membrane, then this moisture will enter into the pores of the membrane, and which will block the pores, and which will offer the resistance to the passage of the air through the pores. And hence hydrophobic membranes, which will repel the water to enter from the the pores of the membrane. And hence hydrophobic membrane is to be used for gas separation. And here also hydrophobic membranes are widely used for these hydrophobic material of the membrane are extremely chemically stable, which can not only withstand high temperature, but also high range of pH also, 1 to 14. And hence, these membranes are used for such application. However, these membranes can be made hydrophilic by treating it with water and alcohol solution. And then once you dry it, again it becomes hydrophobic. As you know that these materials, these membranes are made by stretching the polymeric material. That means once the membrane is cast out of PVDF or polypropylene or poly PTFE, it is stretched to form the specific structure of the membrane. And as you know that for air filtration, it requires to understand the uh, Brownian motion of the air through the membrane, and hence hydrophobic membrane are widely used for gas separation, air filtration, air sterilization, or for that matter, high value, that means at high pressure, the membranes are used for separation of gas mixture, because at high pressure, the diffusivity of the gas components create the variation between the different components. The transport and reaction phenomena that take place in multi-layered, again mixed matrix membrane. As you know that membranes are getting research day by day and creating new forms of membrane, new material of membrane, and new types of membrane based operations. Whether it is mixed matrix membrane made up of different materials of membrane to bring the benefits of different materials and offer only single solution to the different operational parameters. Similarly, multi-layered, it can be single layered, it can be multi-layer membranes, along with activated carbon sorb that can expect to improve the extracorporeal blood purification. In basically, a model is developed that aims at the description of the removal efficiency of hormone. This is again another example of membrane material or membrane separation process in purification of blood, that is in dialysis, and in that a particular component uremic toxin from the blood can be separated using a special design of the membrane, which is made up of different layered membrane as well as different material of membrane, that means mixed matrix membrane and different layered membrane. Basically, as you know that uh, otherwise the dialysis is a very cumbersome process as well as very expensive process. Membrane has helped lot in creating the system which will not only reduce the cost of dialysis but also improves the performance of the dialysis in blood purification. And this carbon adsorptive particles on the multi-layered matrix membrane has come in picture considerably. And hence when we talk about the application, whether it is crystallization, whether it is basically gas separation, whether it is biological separation, that is in terms of membrane bioreactor, membrane purification, or understanding the CFD structure is extremely important as far as the process is concerned. And hence, when we talk about the modeling and simulation of membrane, it gives us uh, great aspect of understanding the membrane morphology and the interaction within the components of the different system. If you understand now that the membrane application is useful or it becomes viable when we understand the nanoscale interaction between solute and membrane material. As you know that the interaction results in the separation or rejection of that component. It can be basically under preferential sorption. It can be under preferential sorption capillary flow mechanism. It will get preferentially sorbed over the surface of membrane, which form the multi-layer thickness having 2 times thicker than the pore size. And under pressure, it gets diffused through the pores of the membrane under capillary mechanism. and hence it is called preferential sorption capillary flow mechanism. As you know that sometimes this interaction is also not preferred, because some of the important molecules, say, which are not required to be passed through the membrane, but still they interact and attach to the surface of the membrane, which is nothing but adsorption, which is also creating fouling as well as concentration polarization effect, and which will not only resist the flow through the membrane, but also it will consume the uh, what you call efficient surface area of the membrane, and hence this interaction is uh, not preferred, or not liked, and hence we have to understand this interaction. Once we understand the interaction, then only we can take the corrective action. Third aspect is basically, if we talk about the process design, we have to understand the flow mechanism over the surface of membrane. As you know that this is a typical application of say fluid dynamics or hydrodynamics over the surface of membrane, where the liquid is flowing tangentially to the surface of membrane. The solutes are trying to interact with the surface of membrane. Similarly, the separation is also taking place. Fourth is selective separation and passage with mass transfer is also taking place. And hence, the combined impact of all these parameters happening over the surface of membrane will decide the selectivity and permeability of the membrane, and also which will decide the performance efficiency of the membrane. The performance efficiency depends upon the this will decide the membrane area per unit volume that is required, and the operational parameters such as fluid velocity, transmembrane pressure, and other parameters will decide the size of the engineered product of the membrane. And once that is decided, then it decides your control parameters. As you know that during the membrane operation, 5 parameters are required to be controlled. One is the feed flow rate, transmembrane pressure, temperature, pH, and the recovery rate. As you know that if we try to have higher recovery rate in the permeate, then we tend to use the more um, transmembrane pressure. And as you know that the more transmembrane pressure has the impact of compaction on the surface of the membrane, which may create the irreversible damage to the membrane. As you know that not only understanding the membrane surface, its morphology, its interaction at nanoscale, its hydrodynamics, as well as the electroscanning microscopic structure, the membranes are required to be tested for its integrity before use and after use. As you know that membranes are used for very sensitive applications, whether it is protein, antibiotics, virus, concentration, sterile application. The membranes are required to be tested for their integrity. And as you know that whether the integrity of the membrane ensures whether the membrane after use is having its structure integrated. That means there is no impact of the operation on the structure and the property of the membrane. And when we undertake this integrity testing before use to ensure that membrane is intact, and after use whether the membrane can again do the same performance, is the integrity test. And as you know that since membrane is used for also sterile application of liquid and gas, so it has to be uh, tested for its retention ability, and that is called bacteria challenge test, which is a destructive test and which is approved by world World Health Organization. That means 1 square centimeter of membrane, when it is challenged by the Pseudomonas aeruginosa of the concentration 10 to the power 7, such a high concentration of bacteria is challenged over 1 centimeter square of the membrane. And on the permeate side, there should not be a single appearance of any microorganism. And hence, this is the destructive test. But every time you cannot do these destructive tests because you lose the membrane. And hence, non-destructive tests are developed using again the computational facilities in terms of integrity test. And that is called bubble point test, air diffusion test, and pressure hold test. The bubble point test is the one which has the correlation with bacteria challenge test, destructive test. All the three tests. In the bubble point test, the hydrophilic membranes are wetted with the liquid, and the air is forced to pass through this wetted membrane. Wetted membrane means the membranes pores are filled with water, and hence when we try to increase the pressure of the air trying to pass through, force through the pores, its solubility it first diffuses, but at particular point of pressure, the largest pore on the membrane surface will open completely, and then the air will start flowing through this open pore very easily, and hence it is called, at that point it is continuously bubbling on the other side, and hence it is called bubble point pressure, which ensure, say for example, pore size of 0.2 micron is having bubble point pressure of say 2.5 bar or kg per centimeter square. If after use the membrane has higher bubble point than this, it is okay, it is having integrity. But if it has the less bubble point than the designated bubble point value, then that means the membrane structure is damaged, and hence it gives you the pore size and thickness of the membrane. The diffusion test is more sensitive. That means again the wetted membranes are challenged by the air at pressure which is 75% of the bubble point, and hence the air is trying to diffuse through the every pores of the membrane which is filled with water. That means it is diffusing through the uh, water in the pores, and which is measured on the downstream side. The diffusion is more sensitive because at every pore the air is challenged. Rather, the every pore filled with water is challenged with air, and hence the diffusion through the membrane is basically measured as a air diffusion test. Now, if the specific value is found out experimentally and also by instrumental method, and which is now specified with respect to pore size, and hence before use, if the membrane is having the same value of air diffusion rate per meter square of area of membrane per unit time, then it is considered to be okay. And after the use, that means after you use it for filtration, for concentration, for separation, for fractionation, once the membrane is cleaned and again tested for its integrity for air diffusion, if the diffusion is less than the designated point, it is okay. But if it is more diffusion rate is found, that means some of the structure of the membrane is damaged, and hence the more diffusion is taking place. And hence the diffusion test is again correlated with the pore size and with the thickness of the membrane, and hence it is also connected with the bacteria challenge test, that is the destructive test. Similarly, pressure hold test is yet another integrity testing of the membrane. That means when you again wet the membrane with water, and it is again the downstream side is closed, and the feed, the air is applied, which is at say water or air, anything can be applied on the upstream side, and the pressure is measured. We have to apply 75% of the bubble point pressure and let it settle down for maybe 10 minutes, and the decay in the pressure is measured. This decay in the pressure is due to leakage, whether it is leakage in the system, that means in the fittings, housing, o-rings, or it is through the membrane. If the decay rate is specified for every pore size of membrane and the area of the membrane. If the now next time, that is after the use of membrane, if this pressure hold test is conducted for checking the integrity of the membrane, then in that case, the pressure, if the decay is faster than the designated value, that shows that the membrane is having some damage during the operation, and hence it is not having integrity. This all test, bubble point test, air diffusion test, water or air hole test, they are basically non-destructive tests, but they are having correlation with the destructive bacteria challenge test, and hence we have to understand the application of membrane is a typical understanding of nanoscale interaction, nanoscale operation, mass transfer under pressure through capillaries, and selectivity and permeability. As you know that new and new membranes are being developed, the materials of membranes are being developed, the structures are developed, properties are developed, then multi-layered membranes are developed, multi-matrix membranes are developed, and which are basically characterized for interaction at nanoscale, hydrodynamic property, feed velocity, effect of transmembrane pressure on selectivity and permeability of membrane, and overall performance of membrane. As you know that the life of the membrane depends upon how long the desire or designed permeate flow rate is maintained. If the permeate flow rate is getting reduced, it will decline over a period of time, but not as fast as dead end pressure filtration. As you know that in dead end pressure filtration, the filter gets immediately blocked because of the separated material over the surface of membrane. Whereas in cross flow filtration process or transmembrane pressure, due to transmembrane pressure, or the membrane which is under which the feed is tangential to the tangential flow filtration, the membranes are having basically, the asymmetrical membrane is having thin layer over the surface of membrane supported by the porous structure. That means the resistance to the flow is concentrated to the only thin layer of the membrane in the thickness of the membrane, and that is called asymmetrical membrane. Further, the permeate rate is maintained for a long time at the desired level due to this cross flow filtration process, in which the feed is tangential to the surface of membrane, and the membrane surface is kept clean because of this transvelocity, and hence the permeate rate in cross flow filtration is maintained for at desired level for quite some time. But as you know that slowly the fouling takes place on the surface of membrane, and hence the permeate rate is slowly gets declined. If it goes below the certain level, then the membranes are required to be cleaned. The beauty of membrane filtration and the dead end filtration, the difference that the dead end filtration, you cannot change the what you call cake thickness, as well as you cannot clean the surface. You have to stop the operation. Whereas in membrane filtration, during the operation itself, the membrane surface is getting clean because of the cross flow velocity. Moreover, membrane operation can be stopped, and then membrane can be cleaned so that its original performance parameters are restored. The permeate rate is restored under the designated optimized operating conditions of feed flow rate and the transmembrane pressure, and hence membrane can be reused again batch after batches in industry. And as you know that if the membranes are maintained under standard conditions of operation, it can have the life as high as 4 to 5 years. That means it reduces the replacement cost, it reduces the losses, it pays back because of the energy saving. It pays back from the recovered water which is recycled for reuse. It also is very impact. And as you know that the same equipment or same unit can be used for conducting microfiltration using microfilter membrane, ultrafiltration using ultrafilter membrane, nanofilters, and reverse osmosis. Depending upon the operation that you want to conduct, whether it is say only separation of the product, or whether it is filtration, whether it is concentration. In concentration, as you know that the feed becomes slowly concentrated because of the separation of permeate from the feed, and hence it can increase its concentration. And as you know that, for example, if you want to concentrate any solution from 5% to say 65% or 75%, 90% of the water is to be separated either by evaporation, if you use evaporators, to reach the concentration up to 50%. That means the dilute solution consumes more energy for water separation, and hence membrane is used for pre-concentration application, where you can separate water considerably to reach the say 25%, and from 25% to 75%, only 20% water is to be evaporated. Or for that matter, now membrane distillation has come in picture, which can remove all the which can achieve the concentration at much below the boiling point temperature. And hence, when we talk about application of membrane in energy saving, we need to understand that this is the process which can now replace, either in association or in totality, the downstream operation. The downstream operation, as we understand that the major cost of production comes from downstream operation for purification, concentration of the product, and hence we have to understand the replacement cost of membrane, which is, and as you know that the controlling the fluid dynamics over the surface of membrane is again reflected in the designing of the piping and controlling the measuring and controlling the parameters. We can not only measure the transmembrane pressure, fluid velocity, that is feed velocity, concentrate velocity, permeate flow rate, but also we can measure the temperature, and we can measure the cumulative separation of the permeate as a mass flow rate in the membrane operation. By understanding the membrane process, membrane morphology, membrane's transport phenomena, we can create the most optimal and most effective membrane separation process for high value product concentration, fractionation, and so on. As you know that, since the same unit can be used for microfiltration, nanofiltration, ultrafiltration, and reverse osmosis, it has replaced filtration, centrifugation, or distillation or extraction, such large concept. And one important aspect of membrane is basically it can be tested for integrity before use and after use. Similarly, it is at ambient temperature operation, so it saves a lot of energy, and it has replaced the sterilization. If you understand, the biological process requires a large quantity of liquid, that is the raw material, to be sterilized before it is sent into the fermenter. Now, whether it is, for example, penicillin manufacturing, so antibiotic manufacture requires a glucose, high concentration glucose solution, large quantity to be sterilized, or urea or nutrient material, and so on. And that is done in the conventional process by heat, continuous sterilizer, which is in which the liquid is heated to 121-degree temperature by steam, and which is held there for 30 minutes, then cool it down, and then send it into the fermenter. But it requires the big investment in heat exchangers, piping, because you have to hold it for 30 minutes at temperature, and then cool it down by passing through the long pipes, and so on. So basically, the heating, holding, and cooling system is used for continuous sterilization in conventional methods, which is very energy intensive, capital intensive, and the important aspect is this sterile liquid is not tested for its integrity, and hence there is possibility, because of the flashing effect, there can be a blockage in the piping, and which will stop the supply of nutrient into the fermenter intermittent. In order to avoid all these things, whether it is gas separation, that is air sterilization, or liquid sterilization, membranes are used for in the upstream processing in every now biological process or fermentation process. Air filtration sterilization is done by hydrophobic PTFE membrane having 0.2 micron pore size, replacing the big what you call depth filters and heat exchangers just close to the membrane. This 0.2 micron membrane filters can be installed. Similarly, in the upstream processing also, the liquids which are to be sterilized using thermal is now sterilized using 0.2 micron membrane. But of course, there is pre-filter also for before 0.2 micron membrane, because 0.2 micron membranes are to be used only for sterilization of the liquid, which is basically removal of uh, 0.2 micron size microorganism. In order to protect its blocking effect, we have to use the pre-filter. So pre-filter, maybe 1 micron size, pre-filter and final filter combination can replace the entire heat exchanger, piping, holding system, and transport system on the upstream side. And hence, membranes is a technically alternative to whether it is sterilization of air, sterilization of nutrient media and water, and in upstream side, uh, and also in fermentation, and then in downstream processing. And hence, I feel that understanding these applications have not only created the opportunity of understanding the application at nanoscale and dynamics, molecular dynamics at the membrane surface. I feel we can use some time for interaction, question answer, and to get ourselves updated with this new technique, as well as what you call uh, um, new chemical processes in which you can really integrate the membrane with the great application, whether it is membrane bioreactor, pervaporation, distillation, membrane assisted crystallization, and so on. So I feel that it will be a great help for for us to update our new design concept of chemical process industry. Thank you very much.
Thank you, sir. Now, if any participant is having any question, please ask.
Hello. Yes. Sir, I take minute and call घेतो है. Just a minute. Yeah. Yes, please. Okay. Yeah. 8, 9, and 10. Okay. 8, 9, and 10. Huh? Yeah. Okay. I can make it actually. Yeah. Right. Very correct. Okay. 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 I will do that. I will do that. Thank you. Thank you. Sorry. Please, if you have any question, it will be
There is one question in chat box.
just a minute.
How can we reduce the cost of membrane separation process?
Yes. Am I visible? 1 minute. Yes. As you know, the cost of the membrane depends upon how efficiently you optimize the operating parameters while designing the system. Whether you choose the right material of membrane, right module, then you optimize the parameters, operating parameters, and you maintain the membrane operation to the desired parameters, such as cleaning of the membrane, then sterilization of membrane, and maintaining the transmembrane pressure, fluid velocity, and so on. And hence, by conducting the operation under optimized condition, you get not only the desired performance for long time, but you reduce the replacement cost of the membrane. And hence, we have to. This is the technology which has come in picture for solving the what you call energy issues, because most of the chemical operations are energy intensive. So basically, membrane is offering techno commercial effective alternative to save energy, to reduce the footprint, to reduce the investment cost, and also operation cost. So operation cost, when you get the best life performance of the membrane, you will get the cost of say membrane replacement and operation will get reduced.
Sir, there is a second question.
Yes.
Can you please explain CO2 capture using membranes?
As I explained that membrane is used in such a way that on one side of the membrane CO2 is passed, and on the other side of the membrane the solvent is passed in co-current direction. As you know that the membrane material which has the selectivity and permeability of CO2 will allow CO2 to pass from the gas stream into the through the membrane into the solvent, and then it gets either reacted or dissolved into the liquid, and that will not only separate CO2 but it will recover CO2, and then this CO2 is recovered from the solution and is stored and is then sent for its application, sequestering. As you know that CO2 capture and sequestering has really made great impact on reducing the greenhouse gas effect, as well as uh, as well as uh, uh, it is a good feedstock for manufacturing of number of chemicals.
Thank you, sir. Now there is, sir, another question. There is a more than 75% of water going as a reject in RO treatment. How can we reduce that?
Basically, we have to understand whether the RO is meant for what. As you know that RO is to be used for desalination of water. That means having very high salinity, whether it is brackish water, sea water, where you want to reduce the salinity to the desired level for drinking purpose. Say if it is less than 500 ppm, the TDS, then it is called potable water. But nowadays there are many domestic water purifier employing RO, and as you know that sometime RO is used for is removing the dissolved substances also, which is otherwise required for our health, and hence RO is not required to be used where the TDS is less than 500 in normal our drinking water supply. If RO is to be used for high desalinated water, then there is required to be balance between the recovery and the operations. as you know that if we have higher permeate rate, then the recovery is higher. For that, you have to maintain high transmembrane pressure. But high transmembrane pressure will damage the membrane due to compaction effect, and hence there should be balance between applied pressure, recovery, and permeate rate. In normal cases, the recovery is maintained between 50 to 60%. That means the concentrate is 40 to 50%, which is sometimes called reject. But however, it is not very high saline. If it is very high saline water, then which is getting concentrated, which you can send it to lagoon process, and by evaporation method also you can recover the salt also from that. But if you see, desalination using RO is done for seawater and high brackish water, and not for drinking purpose, which is normally the matter of concern. In recent days, the Green Tribunal was there, and RO manufacturer went to High Court or Supreme Court, and they asked the Green Tribunal has asked this manufacturer not to use RO because of the lot of reject, which is wastage of water, and hence it is understood that RO is not at the fault. The application at the wrong place is to be avoided. Thank you.
Thank you, sir. So next question is, can we regenerate used membrane like we do regenerate used catalyst?
Oh yes, I explained in my lecture that uh, as the membrane performance goes down because of the fouling effect, one can always regenerate the what you call membrane performance by cleaning it using either there is enzyme solutions which will reduce the surface tension at the surface of the membrane, and then will clean the membrane completely. Or it can be cleaned during the operation by reversing the flow, or it can be cleaned by sending the liquid from the permeate side for microfiltration membrane and so on. So there are different types of cleaning methods to regenerate the membrane, and it can be again and again reused for years together. The life of typical membrane is sometimes 4 to 5 years.
Thank you, sir. Sir, last question is, what is the new trend in the designing of membranes for dialysis?
Yes, the new trends is basically is to use the multi-layered and multi-matrix membrane. That means the membrane materials of different polymeric materials are used, so that it's what is the basic of it. It should be thermally, mechanically, biologically, chemically stable. Similarly, it should have the surface morphology such that there should not be any adsorption effect. Similarly, it can withstand any temperature pressure. But in dialysis, you need very sensitive and high performance, as well as the structure should be extremely smooth in order to give higher permeability, so that the dialysis time is reduced, the efficiency is improved, and as I told you that uh, from the blood also it can selectively separate the impurities, and that is by developing the structured membrane. And this structure can be developed by creating the composition, or say composite membrane material. Thank you.
Thank you, sir.
Okay.
And now I request Professor Unmesh Patil, sir, to deliver vote of thanks.
Hello, good morning everyone. It's great honor and privilege to propose the vote of thanks on this memorable occasion. We are honored to have eminent speaker today, Dr. V.S. Sapkal, Professor Sant Gadge Amravati University, Amravati. Sir conducted the session on computational methods in chemical engineering. He enlightened us with starting with the today's process industries, then importance of biodegradable products, then computational techniques for separation methods, introduction to membrane separation processes, advances in membrane technology, computational characterization of membrane, understanding fluid dynamics to investigate module performances, kinetics of immobilization process on membrane surface, performance prediction of mixed matrix membrane, material design of membrane applications, modeling of membrane separations, optimization of membrane bioreactors, membrane morphology at nanoscale, and so many important things. Sir, you are very kind towards us whenever we request him to conduct the session in workshop or FDP in spite of his very busy schedule towards number of responsibilities at national level. Sir, you are taking time for us, sparing time with us, and giving the valuable time for conducting the sessions and enlightened us with the knowledge. We are very much thankful to you, sir, and hope that this association will be continued in future. Thank you very much, sir.
Thank you. I also express my sincere thanks for making me associated with your program, and also uh, good interaction. And I hope that we all chemical engineers will contribute in furtherance of the knowledge in specialized fields, so that it will not only make the industry better, but also the life standard better. And that is also the core of new education policy, and where we need to combine innovation, research, and excellence put together will really make chemical engineers great. So I also thank all the participants, as well as you in person, and institute also, and as well as authorities from Batu as well. So I thank everyone connected with this program. Thank you.
Thank you, sir.
Okay. And let us meet in future as well as on such occasions.
Yes, sir, definitely, definitely, sir. Thank you very much,
Okay.
sir.
Thank you. Okay. Thank you.
Thank you, sir. We'll start next session at 1 p.m. So please be online before scheduled time. Thank you. There is one announcement. You can give your feedback for the present workshop on AICT Atal website.
You can give the feedback through your login. Okay, so everybody can log into your Atal portal and go to the feedback column. You will find this workshop with ID 752, and here you can give the feedback.